everyone, welcome to our video, and in today's video we'll discuss about IDOC, the integrated dual output converter, which is a topic that was written and published in a paper in 2017. Before proceeding, I would like to tell you the problem statement that we are trying to solve here. So in a battery or a solar panel or any other DC source, it gives one voltage at a time. But many systems, complex or simple, may require multiple voltage level. In automobile, there are sensors that works on 5 volt, 12 volt, and 3.3 volt system. So how will you provide multiple voltage level? In AC, it would have been easy. You use the transformer, change the ratio of the primary and secondary windings, and get the required output voltage level. So we use the same topology and concept. So instead of transformer, we use the DC-DC converter for it. So the schematic and the connections are the DC source, the positive and negative line gets is given as input to the DC-DC converter, and the output is taken on the resistive load side. So this resistive load can be your 5 volt system, your 12 volt system, your input to a microprocessor chip, or anything. The types of DC-DC converter are buck converter and boost converter, and a variation of the same buck and boost converter. Now the converter do not magically generate or change voltage. What it does is it stores energy in the form of inductor and capacitor in the form of magnetic energy, electrical field, and battery, and releases it in a timely manner. So when you take the average of the voltage in those time period, it will give you the voltage across RL, which is the required voltage level, a step up voltage or step down voltage. So just a quick recap, we'll take a quick recap on buck and boost converter. So a buck converter, here is the schematic diagram, the DC input source, switch, freewheeling diode, inductor, capacitor, and the resistive load. In on condition, the diode act as a reverse bias, and the flow of current will be the one that is shown and marked in blue arrow. So the mathematical equation are shown on the text right here. During off condition, this switch is open and this diode will act as a forward bias, and the inductor will act like a battery, because since it does not like a change in flow of current, so it itself releases its stored magnetic field energy in the form of electrical current. The output voltage and the current through the inductor is shown in the mathematical statement here. Coming to the boost converter, which is step up voltage, the schematic is the one like shown here. There is an input V, input DC source, inductor L, switch S, diode T, capacitor C, and resistive load RL. In on state, the switch acts as a short circuit and provides least resistance path for the current to flow. It charges the inductor and stores the energy in the form of electrical field. The change in the inductor current is the shown mathematical statement on the right. In off condition, the switch acts as an open circuit, no current flows through this loop, and the inductor and the battery voltage V in is show it gets reflected on the output side, and it acts as a boost voltage. The inductor current V output and the duty cycle D, the mathematical statements are shown here. Now the question is, can there be a system where we require two voltage, one higher than the DC input and one lower than the DC input at the same time? The answer to this question is yes, which is getting increasingly popular in the field of power electronics. So this is where this paper comes in handy. So this paper, the title of which is Experimental Analysis of Conventional Buck and Boost Converter with Integrated Dual Output Converter, is written by Sriramalakshmi Palanidoss and Vishnu Theja from VIT University, Chennai. This paper is cited in 24 papers and has full 6,663 full text views. Now, if you see what is written in the paper, is the demand of integrated converters is increasing day by day, and over conventional converter, and SIMO topology, single input and multiple output, has found much advantage in terms of reduced number of switches. Applications of IDOC are electric vehicle, LEDs, USB, power managers, small projector, HID devices. So this is how IDOC circuit looks like. So you have a single DC supply VN, series connected switches S1 S2, and two inductors and capacitors L1 L2 C1 C2. The output voltage are taken on VO1 and VO2, and there is a diode D. Now the converter can be operated in three different modes: and at high switching frequency. So what are the modes of operation of IDOC converter? But before that, I would like to tell you. So if you look at the circuit, so this top part of the circuit looks like a boost converter, where this side of the circuit looks like a buck converter. So the topology of IDOC has been taken from a boost converter and has been modified a bit. So now let's look at the mode of operation. So this is mode 1 of operation, where both switch S1 and S2 are switched on, and this is known as shoot through, which is kept intentionally so that the current drawn from the V in is continuous. So now in mode 1 of operation, when both switches are switched on, it provides a least resistance path and the current flows through this loop, and some of the current goes through L2 and is shown at the output VO2 and can be taken, the output voltage can be taken at VO2. Now in second mode of operation, the S2 is open and the current from V in, the current is drawn from the V in and is flow, and the current flows through L1 inductor and D, which is now forward bias, and the output can be taken at VO1, which will be a boost voltage, and at the same time the current will flow through L2 as well, and the output can be taken at VO2, which will be a step down voltage. In mode 3 of operation, the S1 is switched on, there will be no current flowing through this loop, and both L1 and L2 will be discharged. The L2 will be freewheeling through switch S2, which is switched on during this period, and both L, as mentioned before, L1 and L2 will get discharged and the output can be taken at VO1 and VO2. So if you have noticed, in all the modes of operation there will be a continuous draw of current from V in. There won't be a stop and go of the current. So this is where the advantages of IDOC comes in. It is obvious it can provide two both voltage. It is obvious that it can provide both buck and boost voltage simultaneously. Also, it can provide continuous input current. The IDOC is best suited for application where multiple output voltages are needed with a single input source, and those levels can be adjusted accordingly. So here is an LT spice simulation for the same. Here there is a boost converter, buck converter, and IDOC converter, and the outputs are taken. So if you see the boost converter, the buck converter and IDOC, the parts of NMOS and diodes are kept same for the reference purpose. If you see in IDOC, the boost voltage and current are around 50 volt and 85 amp, whereas in boost converter standalone it is around 66 to 72 volt with a large amount of ripple and current which is in the rate, which is in the order of kiloamp, which is actually high. And if you take the buck side, if you see the buck voltage is around 11 and the buck current is around 9 amp, and in this the buck current is around 9 amps and the buck voltage is around 7 to 8 volt. So we are both getting higher buck voltages and also the higher and lower, I would say here, the boost voltages, but the currents and other things are in order with lower amount of ripples. So here is what the efficiency comes into the picture. So what is the conclusion? So simultaneously buck and boost operation can be done. Continuous input current good for the battery, heat, less ripple, and predictive thermal behavior. You can predict the thermal behavior in such cases. Better predict the thermal behavior in such cases rather where the current stop and go, where the thermal prediction will be difficult. Smaller PCB area save the cost. Less switch stresses increases the life of the parts. Higher efficiency and safer shoot through. So this is where the conclusion comes in. I would like to add, batteries don't fail because of the voltage. They fail because of how the current is drawn from them. Now in conventional buck and boost converter, they pull current in sharp pulses, creating heat, stress and cause long-term damage to the battery. This is where the IDOC converter changes that by sharing energy between buck and boost output and maintaining continuous inductor conduction. It draws smooth, steady current from the source. Makes it ideal for the batteries, electric vehicle, and renewable energy source and compact power electronic sources as well. Instead of using two separate converter, IDOC delivers two voltage simultaneously with fewer component and higher efficiency. And most importantly, it does it without hurting the battery. So that is why both from an engineering perspective and system level perspective, the IDOC battery loves IDOC. So this is what I concluded from the paper, and the result from LT Spice simulation shows the same. Let me know what you think about this paper, and if you have any thought about it, please write it in the comment section below. Thank you. Have a good day.